Come on, boys, give it all you got. Show them what you're made of.
Huh, what am I made of? What's the ball made of? What's everything made of? Trying to figure out what everything is made of has been going on for a long time, and we're going to look at some of the progress that's happened over a large amount of time. First, we're going to go all the way back to Aristotle, who thought everything was made of fire, earth, air, and water. He was on the right track looking at elements, but we know there's a lot more elements than just those four. And it's hard to pull those things out of other materials, to pull the element of fire or water out. So what we started looking at was what you can break things down into. This is where the term the atom started being used, and it was talking about indivisible parts. So if you break material like a piece of wood down to the smallest pieces, what is the smallest part that you can't break down anymore? That must be what's making up that material, and we want to figure out what those indivisible parts are. So we'll start with Dalton, who had the bowling ball model. So if you break everything down, they come in these really small spheres of different types that make up everything. This is called the bowling ball model. And it was nice and simple. However, the next progression came in that we noticed that things have charges. For example, you may have rubbed a balloon on your head and it builds up a static charge. So charges need to be involved in these atoms that make up everything. So Thomson looked at this and came up with the raisin bun model, where there's a positive sphere, which is like Dalton's ball from before, and these little negatives just kind of stuck into it like raisins in a bun. But we kept doing experiments on the atom, and Rutherford did this gold foil experiment. He took a very thin sheet of gold, and I've put the picture of an atom there, so that's what we think gold is made up of those atoms. And then he shot what's called an alpha particle at it. So you can think of taking a gun and he's shooting this really heavy alpha particle at it. You don't really need to know what an alpha particle is, but an analogy I've heard of this experiment is like sending a bowling ball at a piece of tissue paper. You're sending something really heavy at what you think to be fairly light and spread out. And so when he did the first experiments, it went through and it kind of curved a little bit from the charges like they were going to expect. And they were just trying to learn more about those charges. But then the weirdest thing happened is they shoot this particle and expect it to just go through like it always had been before, and it bounced off. Again, the analogy has been made if you send a bowling ball like a tissue or a Kleenex, and it bounces off. This was nothing like what they expected. And so what this means was the whole mass of that sphere that Dalton and Thomson were talking about had to be localized into something very dense and very heavy. So we're gonna go to this model and said instead of taking up that whole area, most of its mass is in something very heavy and dense in the middle. And we replaced it with this model, where there's a very heavy nucleus in the center, and then the rest of the charges are orbiting around the outside. So round the outside, round the outside, round the outside. So the notes popping up here, there's a very small, very dense positive nucleus in the middle, and we have far orbiting electrons, which are the negative charge. The weirdest thing to conclude about this is what's in the middle, and the answer is nothing. Not even like air just filling up that, but absolutely nothing is in the middle. Now this takes up the majority of the atom. It's not actually like this close. If we were to put this into reference for things that we're familiar of, if you blew up this atom to the size where the nucleus was a basketball, the electrons would be kilometers away, like super far away. So this is not like just like a balloon with like a marble inside of it. It's so spread out, and most of it, the far majority, all of this area is just nothing. Now again, you might think like, well, who cares? But remember, you are made of atoms. You have mass, you're made of atoms. So your hand is like this. It's got these tiny, very heavy nucleus, but there's nothing in between that. So your hand is mostly hollow, and your other hand's almost hollow, and they should be able to just pass through each other. But the only reason they don't is because of those repulsive forces of the electrons in the nucleus pushing away that you can't push your fingers through one another. But you're mostly hollow. And you might be thinking, well, can I get rid of that hollow space? Well, you hope not. That'd be very bad for you. But there are things that exist that have the nuclei right next to each other. And this is called a neutron star. And you have the mass of like a whole bunch of stars, or our suns, into the size of about a city, because it's that heavy, because all the nucleus are together. So I find that mind-blowing. I hope you enjoy that fact that you are pretty much hollow when you look down to the size of an atom. It's really weird. The next progression comes with Bohr. And so what he kind of found out was that there is electrons existing at distinct energy levels. This is also really weird, and you learn more about this in Chem 30, but basically it means we can have an electron here, we can have an electron here, but you cannot have an electron in the middle. And scientists did some experiments with light and spectrum to figure that out. Again, that's all coming later in later chemistry courses. Right now you just need to know they come in shells, and there's also a neutron in the middle. So we have protons, neutrons, which just has no charge. They're both really heavy in the nucleus, and then we have all these very light electrons orbiting around at specific shells. So that's what everything is made of: protons, neutrons, and electrons, and these different rearrangements. And so when we look at all of matter, they're all made of these different things and different numbers of protons, neutrons, and electrons. And so to organize these, this is the periodic table of elements. Element is the word for one type of atom. And it's organized in this chart, which is really well organized. And we're gonna look at a couple of the trends or why it's organized in this way. First thing I wanna note is there are periods and groups. When we're looking at rows like this that go this way, these are periods. And it says right here, we have period 1, 2, 3, and 4. When we're looking at these numbers over here, which tell us the columns, those are our groups. So just write that in here. Groups would be columns, and periods, it said it down there, but periods are the rows. All right, so we might reference, like, in period 1, what are their characteristics? And that's one part of their organization, is that things in the same group, I'm going to put here, in the same column, have very similar characteristics. These are called the alkali metals, okay? And they are group 1, and the similar characteristic that they have is they are very reactive. Hydrogen's really reactive, lithium's very reactive, and as we keep going up, we actually keep getting more and more reactive. If you put sodium into water, it'll just light on fire. Potassium makes a kind of explosion, and you kind of get bigger explosions, even just in water, as you keep going down there. Another group we should be aware of is the group all the way over on this side, which is group 18, which are called the noble gases. All right, and these are kind of the opposite on the other side. They are very, very stable. Very, very stable. They don't react much at all. One I like to point out here is neon. Lots of signs, the ones that glow are made of neon, because you run electricity through them. They're not going to just burst into flame. They just kind of glow that nice color. They're not very reactive. But the big thing I want to look at today is how we can determine the number of protons, electrons, and neutrons from the periodic table. So I'm going to look at an example for lithium. I'm going to look at lithium here. Now I know it's really small there, but I'm going to erase and try and zoom in on that. And it's got two numbers. It's showing us 3 and 6.941. What that means is, first let's look at this number, 3, which means the number of protons. So I'm going to draw what the nucleus is going to look here. We know that's where the protons are. So there are 1, 2, 3 protons in the nucleus. So that's how we determine the protons. Next, when we look at the 6.94, this is going to be some decimal places, but we're just going to round up to the closest number there, which is 7. And so that means it has a mass. That's what that number stands for, the atomic mass. It has a mass of 7. Now remember from before I said the nucleus has the heavy protons and the heavy neutrons. The electrons are not very heavy at all. So pretty much all of that 6.941 is made up of the mass in the nucleus. And kind of works conveniently, every proton and neutron weighs about 1 in this unit. We'll get to those units later. So I have 3, so to get up to a mass of 7, there's 4 more things in there, which has to be the neutron. So I'm gonna write a neutron, a neutron, a neutron, and let's just stick another one in the middle there. So we know 3 protons, a mass of 7, there must be 4 neutrons. Now, lastly, the number of electrons. Since the protons are positive, all elements on their own are neutral. So if it's got 3 pluses, it has to have 3 negatives. So I'm going to draw a circle around with 3 negatives in it like that. Now that's a very rough diagram of what it looks like. We're now going to look at how to draw a more proper version now that we know how to determine protons, neutrons, and electrons. First, we're going to look at the energy levels. Remember, Bohr said they don't exist just all in one orbit. They exist in certain energy shells. So it says here, electrons orbit at specific distances, shells / energy levels. All those words are used. The very furthest orbiting one is called the valence shell, and it has the valence electron. So valence basically just means outside. So we have the nucleus here with pluses and minuses in it. We have some electrons around the outside, and they are going to be in distinct shells or rings looking like this. Now, the number that can fit in each shell is also important. The first one you can think of as being small. It doesn't fit very much. It fits 2. The next one fits 8. And the next one fits 8 as well. So don't worry about like the actual size of them. How they fit, the reasoning is kind of complicated. You'll learn more about that in university. But the big thing you need to know is there's 2 in the first one, 8 in the next one, and 8 in the next one. We're gonna need this to know this for drawing those energy levels. And we're gonna draw them in a Bohr diagram. So there's the steps written out. I'll go through them quickly and then we'll do some examples. So first step is determine the number of protons by looking at the atomic number. That was the 3 in lithium. Determine the number of neutrons by subtracting the atomic mass. That was that number that rounded up to 7, minus the atomic number, which was that 3, and we got 4 neutrons in that last example. Write these 2 values in the center of a circle, showing the nucleus, indicating the number of protons and neutrons. So example, just put P and N with the numbers right there. Determine the number of electrons. For an atom, it will be the same as the protons because it's neutral overall. And then draw the electrons in their shells and fill up those shells with the electrons, going 2 in the first one, 8, and then 8 as we go outwards. For the first level, this is where it gets a little detailed. The first level, you have to pair them in the north position, so in the top spot. For the next 2 shells, they get 8, and they kind of have a north, east, south, and west position. There's gonna be 2, 2, 2, and 2. And we have to put 1 in each spot before they double up. I know that sounds confusing, so let me show you what it looks like. So we're gonna start by doing a Bohr diagram for oxygen. So I'm gonna bring up the nucleus, and inside I need to put the number of protons and the number of neutrons. Now, if we look for the atomic number for oxygen, it is 8. So I'm gonna put 8 right there. So number of protons, the atomic number. Then I look at the mass and it says it's a mass of 16. So that's the protons and neutrons together. Well, if there's 8 protons, how many neutrons do I need to get to 16? It's 8 more. Often for small ones, they're close. They're either the same or just off by 1 for those top smaller elements. So now I have protons and neutrons. Next, we have to put the electrons. How many are there? It's the same as the protons. So there's going to be 8 electrons. But we can't just draw a circle and put 8 randomly. We need to show those specific shells. So I'm going to draw this first shell here. How many fit in there is just 2. And I said put them in the north position, so right at the top. So there's our 2. How many do we have left? We have to draw 6 more. Those are all going to fit in the next one. And this is the part where we have to fill in the order of going around northeast to southwest. So I'm going to start by putting 1 in the north position. 1 there. Now we can't put another one right beside that yet. We have to go to the next position. So I'm going clockwise, put 1 there. So now I'm going to total of 4, 5, and 6. Now there's 1 in each position. So now I start doubling up by repeating those same spots. What total am I at? 1, 2, 3, 4, 5, 6. So I'm going to go 7 and 8. And that's all I needed, 8 electrons right there because there are 8 protons. So that is the Bohr diagram for oxygen. So now we'll do one for magnesium. Again, we put P for protons and N for neutrons in the middle. We look up the atomic number for magnesium and it is 12. That means it has 12 protons. And we look at the mass and it's got a decimal after it, but it rounds to 24. So if the total mass is 24 and 12 of them are protons, 12 of them are neutrons as well. So they're often the same for those elements at the top. So now we have to put the electrons. How many do we have to put? We have to put the same number as protons, which is 12. How many go in the first shell? It's only 2, and those have to pair at the top. So 1, 2. Excellent, we're filled there. How many do we have left to go? We have 10 left to go, and only 8 fit in here. So this one fills up. I'm gonna fill in the right order though. 1, 2, 3, 4, 5, 6, 7, and 8. I'm at a total of 10. I've filled all these spots so far. I need to go to the third shell and put 2 more. All right, so I'm going to put 1, 2. However, that's not right because they're paired, but I need to put 1 each in the north, east, south, and west position before I stop pairing. So let's erase that one there. I need to put that one over here. We don't pair them unless we've already got 1 in each spot. And that's the Bohr diagram for magnesium. Let's do one more for neon. It's protons and neutrons. We look up its atomic number and it is 10, which means it has 10 Protons, we look up the neutrons and it's 20, or rounds to 20, so we have 10 there as well for total mass in the middle for 20. How many electrons we need to put? We need to put 10. In the first level there is 2, so I'll put 1, 2. And the next level fits 8, and that's exactly how many I need to put. So I put 1, 2, 3, 4, 5, 6, 7, 8. Now this has a full valence shell, and that's why, when I was referencing before, neon and all the other noble gases are very stable, because their valence shell, or the most outside shell, is completely filled, and this is what makes them stable. But we'll look at more of those properties in the next lessons, because that is all that we have for today's lesson. So if you could ask your questions in the live time and make sure you apply these concepts to your practice questions, that would be great, and I will see you in the next video.